Welcome to Lecture 18. So our goal is to get our robot to be able to interact with objects in the real world, in this case that are laid out on a table, and we want it to be able to reach out and pick up certain objects and interact with them. Where we ended last time is we had this image that had been labeled, and so we have a number of connected components. What we want to do is figure out where are those components located and what is the easiest way to pick them up. And so we want to find their centroid positions and their orientation. To do that, we're going to have to do some math. And I think you'll enjoy seeing some different ways to parameterize lines. So as a reminder, we started with this picture of these Duplo box, and we wanted to first pick out what is the best value to threshold them, so we can identify objects and background. We did this analysis in grayscale, although you could apply that to colored images. And then we take this grayscale image and we want to figure out what is this optimal threshold value. To do that, we maximize the between group variance, which is actually the same as minimizing the within group variance. And so if we plot this within group variance, how dispersed are these two groupings of foreground and background, the minimum value was a threshold of 161. So we apply that to our image, and now we have a binary image where everything is either foreground or background. Our next step was to find the connected components. We did that with a two-step raster process, where our first pass through here we came up with a bunch of different labels. We actually had 993 labels in the first pass, but there's a lot of things which are connected, and so those are equivalents. And so our second pass, we go through and then we apply all these equivalences. I also slightly cheated because I also removed some noise pixels, these 1 pixels to 5 pixels in the background. I said all those are noise. I actually used some of the statistics we'll talk about today to do that. But I end up with just 9 labels. Once you have those 9 labels on the components, then we want to figure out where are they located. So that is their centroid, and then their moment is their orientation. And so here their centroids are shown by white stars, and their moments are shown by these red lines. So now we know where the center of each of these objects, and we also know which is the long axis, so we can arrange our gripper so that it can grab on either side of that long axis, and hopefully that'll make it easier to pick up. One other thing that I did is I made the length of these lines correspond to how many pixels are in their image, so the mass in pixels of the image. So you see that this is very long for 5 and for 7, but it's short for 6. It's also short for 9, and the reason for that is because we missed a bunch of pixels. So you can see here that this green level is actually pretty light, and so when we threshold that, we lost a bunch of pixels there. And then when I eliminate my noise, then I have even fewer pixels that are actually in this connected component. But it's enough so that we can still identify a good place to pick it up. To be successful in this, we're going to use something that is called an indicator function. And what the indicator function is this nice little compact representation where you say I of object I, and I can apply it to any pixels in my image by specifying their row and their column value. And what the indicator does is we're going to set it to be 1 if the pixel RC is contained in component I. And otherwise, we're going to set this to be 0. Very quickly, we can use this then to highlight only one component at a time. The next concept that we need is the concept of moment. And moments are statistics of our object. They've got a compact representation where this moment, we say M subscript ij, where we can pull out some different moments corresponding to the R and the C values of the object K. And so how you write that is a summation over all of your pixels, so over all RC, and we take R raised to the ith power and C raised to the j power, and then we multiply that by our indicator function, indicator K of RC. And so it's going to take only the pixels that belong to object K, and it's going to raise their R and their C values to some power. Now the first one we have is our M00. I like to think of that as the mu moment. That's going to be the summation of over RC of R to the 0. So it's just going to be 1 times the IKRC. And so what the mu is going to give us is just the number of pixels in my image. And so you can sort of think that as sort of the mass of the the pixel mass, but it's also the area. Next concept that we have is the order of a moment. And the order of a moment is just the sum of I plus j. So m00, that's a 0th order moment. Now we're going to talk about the first order moments. These are very useful for calculating the centroid. And so m10, we're going to do our summation over all rc. And we're going to take the r raised to the first power times my indicator function, rc. And then my m01 of object k is just my summation over all rc. We multiply it by c, and then my indicator function, rc. And so those are my first order moments and my 0th order. The centroid is a center of mass such that if I put all the mass concentrated at this special location, r bar I, c bar I, then the first moments for the object I would not change. And so if I write that mathematically, then I'm going to say I'm going to take the summation of rc, and I'm going to multiply that by this special value, r by I, my indicator function for object I, over rc. Well, that is going to be equivalent to my summation of rc times just my first moment. So that's going to be II rc. So this special value, since this value is a constant, I can pull it out front. And so I get that r bar I of summation over rc times my indicator function of rc is equal to my summation rcr of II rc. And so now I can solve for what this r value is. And so r bar I is equal to my summation rc of II rc divided by summation over all rc of II rc. Well, this top value that I have here, this is just my m10 of k, and this bottom value over here is just my 0th order. And so here we have the definition for what the mean row position is. It's going to be my first moment divided by my second moment. We can write the same definition for my summation over rc of ci bar. That's going to be my summation over rc of c times II rc. And so my ci bar is going to equal my summation of c over II rc over my summation, these are over all rc, of II rc. And so again, this is going to be my m01, so my first order for my c values over my 0th order. And I've got a slight typo here. And then we have our answer. So my next concept is that of central moments, because often it's useful to compute the moments with respect to the object's center of mass. And the reason we want to do that is because then the result is invariant to translation of the object. Whereas otherwise your higher order moments are going to change if you just take your object, and if I move that, and as I move that around, then my higher order moments would be changing all the time. And I really want to know what doesn't change even as I translate this around. Our central moments, instead of using an m, we're going to use a capital C. And then all we do is we take our summation over all rc. Now what we do is we take our r minus our r bar for object k, raise that to the ith power. We take our c minus c bar for object k, raise that to the jth power, and then we multiply it by our indicator function. And then we have our centralized moment. And just to remind you, this r bar, k bar, that is the coordinates of the centroid for that kth object. We want to talk about the orientation of our objects. And so when we talk about the orientation, what we really want to do is we want to put an axis. We want to put an axis through our object so that it minimizes the second moment. And so what I'd like you to do for each of these objects is to try to draw in them the minimum axis. And it's not too hard for this. Along this line here, whereas this object here, I could try to do it here, but now I've got a bunch of points that are very far from this axis. And so it'll work better if I go here than the parts that are farthest from the axis. There's just not as many of them. And so this is a much better axis for here. And so my second moment is going to take advantage of that line parameterization that we had. And so here, this DRC, that is the minimum distance from that pixel at RC to the line. We want to minimize this calculation L with respect to all possible lines. And so to do this, we need a handy parameterization of lines. We're going to use what's called the rho theta parameterization of a line, which says that I completely specify my line by saying it's sum x times cosine of theta, where the theta is one of my parameters for my line, plus y times sine theta minus the point rho is equal to 0. And so we want to minimize the distance. So let's talk a little bit about what this parameterization means. And so right here you can see I have placed a point here, and that point is rho distance away from the origin, and it's at an angle theta. And so in this animation, if you change this rho, you can bring that line closer or farther away from the origin. Just want to show you that you can represent any line in the world by this. It's a little more robust than our slope-intercept equation because there is no divide by zero errors in this. And so it's a nice way to parameterize a line. That's what we're going to use in this because it's quite often that you could have an object that's just pointing straight up and down. So the distance of any random point RC to this line is going to be just this equation here where we put R for the x. R cosine theta plus y sine theta minus rho. And so if it's 0, I'm on the line. Anything else, I'm going to be off the line. And we want to minimize that distance. And so the minimum second moment is this L star value. And so you can see I've put in my D value here, and I'm squaring that, multiplying by my indicator function. So I'm only looking at pixels that belong to the object. And so to find that minimum, we take the first derivative, and then we set it to 0. So just like if we've got some plot, we're going to find the first derivative of this at all points here, first derivative, and we want to find the point where that first derivative is equal to 0. And so we're going to do that for our two parameters. We've got two parameters to look for. We're going to look for rho, and then we're going to look for theta. We could choose either one of these to go for. However, theta looks hard because theta is trigonometric, so we're going to start with the rho. And so we start with our equation for L, and we want to take its derivative with respect to rho. So I'm going to take the d rho, d rho. See, this rho is stuck inside this thing. We're going to have to apply the chain rule to get it out. Let's do one level of simplification first, where we can pull out the summation. So this is equivalent to the summation over RC, and I'm going to put in this derivative here. And I've got R cosine theta plus C sine theta minus rho, quantity squared times my indicator RC. The chain rule says that if I've got h of x is equal to some f of g of x, and I want to take the derivative of it, that means that h prime of x is equal to f prime of g of x times g prime of x. So I'm going to say this entire quantity inside here, that's going to be my g of x, and then my f of x is going to be the square. So I could say f of y is equal to y squared, so f prime of y is going to be 2y. And so I'm going to apply that to my function, and I get that my d rho is equal to my summation RC times 2 times this quantity here, R cosine theta plus C sine theta minus rho. And then my derivative of this internal thing is just going to be -1. So the next thing I have, the summation is linear over here, so I can break up this summation into a number of terms. Got my summation over RC of -2 times R cosine theta, and then I've got my summation of 2C sine theta over RC, and then I've got my summation of 2 rho over all RC. These are all multiplied by my indicator function. Now I can pull out everything here that is a constant, and so my constants is the -2, and then this theta is going to be constant. My r will change. I've got my 2 here and my sine theta, and then my 2 rho. And so that's going to equal -2 cosine theta times my summation over RC of r times my indicator RC. And then my next term is going to be minus 2 sine theta times my summation over all RC times C times my indicator of RC. And then plus 2 rho times my summation RC of my indicator function RC. And so now what I can do is I can apply to each one of these terms, because these are actually moments. And so I get that this is equal to -2 cosine theta. Well, the summation of all r, that is going to be my r bar times my mu value. And this over here is minus 2 sine theta. B, I'm just multiplying my average position times my 0th order. And so that is going to be c bar times my 0th order. And then I've got 2p times my 0th order. So I can pull all these things together. I can take out my common terms, which are -2 m0, 0. Multiplying that by cosine of theta, I'll put my r in front here, plus my sine of theta, put my c bar there, minus rho. And now the next thing we want to do is set it to 0. I'm going to say 0 equals all this. And so since this is equal to 0, I can divide on both sides. And so when I divide on this, I can cut out this, and I have just 0 is equal to r bar cos theta plus c bar sine theta minus rho. And so what this means is I have a line that passes through the location r bar c bar. Okay, let me write that down. So what we know about our second moment line is that it's going to go through the centroid. What we don't know about it is what is this theta that we should have. And so we can take our result from here and plug it into our next equation and then solve for what this theta value is. We're going to do a mathematical trick here where we're going to give us our new coordinate system. And we're going to call it the r bar c bar. We do this because we want the centralized values. It'll simplify our math, and so I'm going to say that r prime is equal to r minus r bar, so I'm subtracting off the mean, and c prime is equal to c minus c bar. And so now we say that this line that passes through L, instead of going through r bar, c bar, it now is going through the point r prime, c prime, both equal to 0. And so it has the equation then that r prime cosine theta plus c prime sine of theta is now going to be equal to 0. And so we've eliminated that rho from this equation, which is going to make it slightly easier to solve. So now we can write that same distance equation that we had before, where we have the summation of RC, and we've got our r bar cosine theta plus c bar sine theta. Remember, this is the distance squared times my indicator function. And what we want to do now is to take the derivative of both sides. And again, we are going to apply the chain rule. So that is equal to 2 times my original quantity, r bar cosine theta plus c bar sine theta, times its derivative. So its derivative is going to be minus r bar sine theta plus c bar cosine theta. These are all times our indicator function. So now we have to multiply this out, and so we've got 2 And boy, that's rather ugly. However, we can clean that up a little bit by using our centralized moment terms in here. So this term here, that is my C20. This term right here, that is going to be my C11 term. This term right over here is going to be another C11 term. And this term over here is going to be a C02 term. And so now I can write these in my terms ofCij's, and I get it's equal to the quantity 2 times, here I've got negative C20 times cosine theta sine theta, and I've got plus C11 times cosine squared theta minus C11 times sine squared theta plus over here CO2 times sine theta cos theta. So I've just copied that solution down here, and now we're going to simplify that by using our double angle identities. So I can replace this entire term here with a cosine, and I can replace this term here with the sine of 2 theta. So let me rewrite that out there. So we're saying the derivative with respect to theta of L is equal to 2 times the quantity of C11 times cos 2 theta plus CO2 minus C20 over 2 times the sine of 2 theta. And so now to solve for what value of theta minimizes it, we just set this to equal 0. So say that equals to 0, and then I want to solve for that. So 0 is equal to... So one of the simplifications I can do is I can get rid of this 2, and then I am going to pull this term over onto the other side. To move this to the other side, it's going to change the sign, so I can do that by just swapping the order of these. C20 minus CO2 divided by 2 times the sine of 2 theta is equal to C11 times the cosine of 2 theta. I want to get all of my thetas on the same side, so I'm going to put sine of 2 theta divided by cosine of 2 theta is equal to C11, and then I'm going to multiply it. So I got 2 divided by C20 minus CO2. Now this, if I got sine over cosine, that is equal to the tangent of 2 theta. And so I could say that 2 theta is equal to tan inverse of 2C11 divided by C20 minus CO2. Of course, that means that theta is equal to 1/2 of tan inverse of 2C11 divided by C20 minus CO2. And since all these terms are moments here, these are all things that I can calculate directly from the pixel image. I do have one problem. If this denominator, if ever my second moments cancel each other, I'd have a divide by 0 error. We don't want to have those. And so although this is what the book says, I would much prefer if your answer that you put in is that theta is equal to 1/2 of the arc tan 2 of C of 2 times C11 and C20 minus CO2. Because if you do that, then you're going to avoid a lot of these divide by 0 errors.